Okay, so we're going to talk about momentum, and this actually comes from the third law of motion. Remember, for every action on an object, there's an equal and opposite reaction on a different object. So this basically comes from that. So momentum gets the symbol P. And the value of momentum is mass times velocity. And the mass has to be in kilograms, the velocity will be in meters per second. And so the units for momentum are kilogram meters per second. All right, I'll do some examples shortly on that. All right, so this is just showing an example of momentum. The more mass or the more velocity or the more of both that something has, the harder it is to change its change or to accelerate it. Basically, requires more force to accelerate it. All right, and this is a big idea in classical mechanics. What we're studying right now, Chapter 1, is all about classical mechanics. And so this idea of the conservation of momentum, and it says, so the total momentum of a group of interacting objects remains the same in the absence of an external force. So this is very useful in for example, people use this in accident reconstruction to figure out, for example, how fast someone was going, and and it's useful for things like really simple stuff like a bullet is fired from a gun. The bullets, you measure the velocity of the bullet, you can tell the recoil velocity of the gun. Again, I'll do some examples of that shortly. Alright, we're not going to do impulse, I think, actually. Hold on. That might be... yeah, that's actually it. Alright, hold on. Alright, so I thought I'd just do some examples. Let's just start out with this idea of momentum. So we have P, momentum is mass times velocity, and the units here are going to be here. Let me just put them below here. So this is kilograms times meters per second, and of course the mass is in kilograms, and the velocity is in meters per second. All right, so here's an example. Suppose we know the weight of someone is, I don't know, how about 675 newtons. Okay, so we know the weight, and we know the velocity. Let's say the velocity of that person is, let's say, 4.2 kilometers per hour. Kilometers per hour. All right, so this will give me a chance to we'll do some we got to do some conversions. For example, the velocity obviously is not in the proper units; it has to be in meters per second. So why don't we start with that? We'll change the velocity to meters per second, and the weight. What we can do with that, of course, is we know that the weight is related to the mass as long as it's something on Earth. So, this is like some person weighs 675 newtons and is moving at 4.2 kilometers per hour. Anyhow, let's work on the velocity first. So the velocity is 4.2 kilometers per hour. And the way that you do conversions is there's several ways to do it, but this is the way it's usually done in in the sciences. Is we know that 1 kilometer is 1,000 meters. I'm going to write 1,000 as 10 to the third. It's the same thing, right? Remember, the metric prefix kilo means 10 to the third, so the kilometer part cancels, right? So those have canceled, and so this is 4.2 times 1,000. Now we have to work on the units of hours. Now notice hours here is in the denominator, right? So I'm going to have to put 1 hour in the numerator, and I know that 1 hour is of course 60 minutes. See, these are conversions that you already know the conversion factor, and then of course 1 minute. Remember, we reserve little m for meter, so I use min for minutes. Is of course 60 seconds. 60. Oops, that's supposed to be it's a 0, not a G. 60 seconds. And of course now minutes cancel, and we had hours cancel. I didn't actually cancel it yet. And so everything, basically it becomes 4.2 times 1,000 divided by 60 divided by 60. Again, that's a 0. Anyhow, I'm going to do that below. So remember, we've canceled everything in terms of units, so the velocity is, let's see, what was it, 4.2? Yeah, 4.2. 4.2. And now it's going to be times 10 to the third is of course 1,000, and then the whole thing is divided by 60, and also divided by 60 again, or divided by 60 squared. It's the same thing. And the remaining units that have not canceled are meters per second. And when you type this in your calculator, you get 1.16, and the 6 keeps repeating, so I'm just going to say 1.17 meters per second. Okay, so we're actually almost done. Let's go back to the weight of the person. So here's of course the weight is 6.75 newtons. But remember, I had this in one of the last videos, that if we know the weight, we know the mass, right? Because the weight is the mass times little g, which is of course 9.8. So now we can solve for the mass, all right? So this, rearranging this equation, we divide both sides by little g, dividing this side by little g, and the little g cancels. And so this whole thing becomes the mass is equal to the weight divided by little g. And I'm going to put the numbers in now. So it's, what was it, 675? 675 newtons divided by, and of course little g is a constant for the Earth, 9.8 meters per second squared. And remember, a newton is a kilogram times a meter per second squared. So when you do the calculation, the mass turns out to be 68.9 kilograms, roughly. And then, of course, we still have to solve for the momentum. That's the original problem. So it's going to be the velocity, 1.17 times the mass, which is 68.9. So the momentum is going to be mass times velocity, so 68.9 kilograms times 1.17 meters per second. I'll leave myself a little room for the answer. Alright, and that is, let me calculate it real quick. So when I did the calculation, it turns out to be, let's see, what do I get? About 80.6. So 80 0.6, and that's of course kilogram, that should be a G, times meters per second. Those are the proper units. And so there's a momentum problem. I'll do a conservation of momentum next.